Hey y'all, welcome back. I'm Mr. Boyd and you're you, and since we're here, we might as well talk about describing quantitative data with numbers. Here we go. On the screen right now are the 7 things we're going to cover in this video today. So let's just get right into it, okay? The first thing is the mean, as in the arithmetic mean, as in add up all the data and divide by how many there are. I don't think that's new to you, but what might be new to you is the symbol that we use right here. Okay, so I'm going to zoom in on that so you can see it. It is X with a bar over the top, and statisticians are very creative people. So the way we say this is X bar. Okay, X bar. Anytime you see that for the remainder of this class, or onward in your academics for that matter, it is referring to the mean of a data set. Okay, what about the mean, or the median, excuse me. The median is just the middle number of the data when they're arranged in order. So what do we do if there are an even number of data points? Let me give you a really simple example here so we can calculate it out. And this one, a lot of people learn at first in elementary school, but it's good to review. Imagine we had the data 3, 5, 7, and 9. They are in order, which makes it a lot easier to find the median. So to find the median, I would usually tick off 1 on each side. If I get to the middle and there's 2 different numbers, all we do is we find the average of those 2. So that would be 5 plus 7 over 2, which is 6. Now y'all look, I fully understand that you know the middle number between 5 and 7 is 6. I'm just demonstrating it here, okay, in case they were 2 numbers that were whacked out decimals or something like that, or if they are numbers that were really far apart. It's also good to know the process. Okay, so let's get rid of that. Resistance. Resistance describes the sensitivity that a statistical measure has to extreme values. Okay, an easy way to think about that is to think about one of my classes that I teach. So let's say that I was having a study session. I had 9 students in the room, and I've made up here for you the amount of money that each of them makes in a calendar year. So this is annual income. So some of them don't work, 4 of them don't work, and so they don't have a job, which is okay because they're in high school. It's totally fine. But 5 out of 9 of them do work, and some work just a little bit and they make $1,000 a year, and some work a little more and they make $3,000 and $4,000. One person works a bit, and so they make $9,000 in a year. So if we take a look at the 2 measures we've talked about so far, the mean, which guys I'm just going to refer to as X bar from now on. X bar is going to be 2,000 on this data set. And the median, which we don't have a symbol for, we always just write median. The median is $1,000. So kind of interesting. One's double the other. Isn't that kind of strange? But that's how it is. Now, to illustrate what resistance is, imagine now that someone with a really high income walked into the room, like somebody, maybe they're a doctor or a big time lawyer, and they make $250,000 a year. That's not 250 and then 0. This is a single number, $250,000. So these were our statistics in the beginning. Now we have our new stats. And if you want to calculate them out to verify, you can, but I've already done it before making the video. So the new X bar is 26,800. And the new median, well, this is kind of a weird feature of the data set I've made. The new median is actually 1,000. So remember what the definition of resistance was. We'll come right back to this in a second. In the beginning, the definition of resistance was how it's describing how sensitive or how not sensitive a statistical measure like mean or median is to extreme values. The extreme value in this case is the $250,000. And so how sensitive were our measures to that? Well, 2,000 became 26,800 and 1,000 became 1,000. Okay, so that didn't change. Better get my dollar signs on here. So what we saw, since the median didn't move as much, the mean moved a lot more. And this is just one illustration, but it turns out generally to be true that the median is more resistant than the mean. That is to say that one big value can really skew the mean, but it has a tendency to not skew the median quite as much. Now, another thing that we have to talk about here is this falls into, sometimes you hear about the average person does this 6 times a day, or the average person brushes their teeth for only 37 seconds. Well, this represents the average person. But keep in mind, the average person is not necessarily a person who exists. For example, look at these data. There's no person in these data that makes anywhere near $26,800. You have the person who makes nearly 10 times that much up here, but $26,800 is nearly triple what any of the students in the room make in a year. So you say, well, but the average person makes 27,000. That's pretty good. Yeah, but that doesn't really describe any of these people. It would make way more sense, add the T on that, it would make way more sense to say, the median of the group is 1,000. That gives you an idea around which a lot of the people are. There's a few people that are at 1,000, a few people a little more, a few people a little less, and then you have one outlier in that 250,000. So always be careful when you hear about the average this or the average that. If you have a data set with no outliers and no skewness, the average is perfectly fine. And we're going to be using the average a lot. But we always have to be aware that it's not very resistant, especially compared to median. And so in some cases, it's not an appropriate statistic to use, at least unless we're trying to be misleading. So that is resistance. All right, range. You already know what range is, don't you? I'm pretty sure you do. Range is just in any data set, it is the maximum value minus the minimum value. What you might be a little bit less familiar with is standard deviation. Okay, now this formula here is the formula for standard deviation. What I'm going to do is I'm going to make up a data set and I'm going to show you a hand calculation and show you how to use this formula. And then, guys, you're almost never going to use this. It's really rare that you need to do this by hand because calculators will do it for you. Microsoft Excel will do it very easily for you. And so it's unusual that you would ever calculate a standard deviation by hand, but we will talk about what it could be used for and how you need to be able to interpret it. All right, so let's come over here and I'm going to make up the data set. I'm going to show you how to use this equation. I'm going to use the same data set from earlier, 3, 5, 7, 9. And I'm going to show you how to use a standard deviation. Now, notice this like x1, this x2, and x sub n all the way down here. What that's referring to is the first number in the list. So that's 3. So that's saying 3 minus x bar. X bar is the mean, which in this data set, x bar is 6. And n is referring to how many numbers in the data. There are 4. So I'm going to get those out of the way right there. So that's 3 minus 6 squared. But you know what, hold on. Let's provide a visual for this as well. The visual for this would be if I drew out a number line and I had 3, 5, 7, 9, and I'm going to include 6 in here so we have the mean. What this is saying, 3 minus 6 squared, it's saying a square that has the length from 3 to 6 as one of its sides. It is a literal square. And that's a 3 by 3 square, so that's 9. Let's keep going. Next part of the formula. So we got to put the plus. So plus the next number. So 5. So 5 minus 6 squared. Let's see it over here. So 5 to 6 is a square. It's a 1 by 1, so it has an area of 1. And you'll notice this calculation, when you square it, turns into 1. This calculation squared turns into 9. Let's keep going. The next data point is 7. 7 minus 6 squared. A square from 7 to 6. And look, my illustration is not very good, but 7 to 6, that's a length of 1, so that square has an area of 1. And then the last one, 9 minus 6, and because I'm just following this, that says last number in the data minus the mean. So that's what I have here. Don't forget to square it. And that is from 6 to 9, so length of 3. That square has an area of 9. So what about the denominator? Denominator is n minus 1, so 4 minus 1, and a square root over top of it. Now the illustration over here should make it pretty easy to see that when I add all of these together, it's 9 plus 1, that's 10, and 9 plus 1, that's another 10. So this turns into 20 over 3 with a square root. Let's see what that is. And I got 2.58. That is the standard deviation of the data set. Now, in some ways, that's kind of a letdown, to be honest with you, because you go, well, 2.58 what? 2.58 inches, 2.58 joules, 2.58 newtons, what is it? It's just 2.58. It's just a number, okay? The standard deviation tells us how spread out the data are. And we can kind of see that here. But notice the more spread out they are, it has this multiplying effect of the squaring. So like this 3 adds 9 to that sum versus only being, so distance of 3 I should say, versus a distance of 1 only adds 1 to the sum. So it's set up to really give a lot of weight to extreme values. And what we would need to know is that if we had another data set with a larger standard deviation, those data are more spread out. And if we had a different data set with a smaller standard deviation, they are less spread out. Let me give you an example of how I would think about this. A few years back in our school district, we used to get data on students' grade level in math when they would come into our school. So math, grade, level. And so we would get the mean. And so let's say that my students come in with an 8th grade, well, I'll make it actually look like a real number. So like 8.2. So on average, 8.2, 8.2nd grade level of math coming in. And the standard deviation is 5.7. So that's one example. What if I had a different, so this is scenario A. What about in scenario B if I found out that my incoming class for one of my freshman classes, their average was a 5.7, so quite a bit lower, but their standard deviation, and I'm using this sigma, although an S sub x is fine too. We'll talk more later in the course about when to use which one. And let's say their actual standard deviation was, like 1.1. So the question is, which of these classes is easier to teach? The thing that most people are going to look for first is they're going to say, oh, well, I mean, the group on the left is higher performing because they have a higher average grade level coming in. But what I look at is I'm actually way more interested in the standard deviation. This class in scenario A, their scores are way spread out, which means there's some kids that are really high performing in that group, and there's some kids that are really struggling learners in that group. And so for me as a teacher, that's actually really hard to deal with because some kids really need to accelerate and some kids need a lot of help catching up. And I'm only one teacher, so that's very difficult. What about scenario B though? Scenario B, that's much less spread out. So so even though these kids struggle a little bit more on average, there aren't a ton of super high achievers and there aren't as many kids that are down really, really, really low. And I can always go down and help the class move. So what I really want in my classes is a small standard deviation because it's much easier to design learning experiences that meet most students' needs. If they're way spread out, it's really hard to design a lesson that meets everybody's needs in a truly meaningful way. But it's a lot easier. So that's an application of standard deviation or something you might start to look for if you ever have access to statistics like this. Because usually people, my experience in education, people just look at the mean. They're like, oh, well, the mean's higher. That's really good. That's going to be awesome. Not necessarily. Yeah, so be careful. There's definitely meaning from that standard deviation. So that conceptually is what it is. My hope is that from this point forward, you're pretty well gonna have calculators and computers do that for you. I do want to talk to you about how you would answer an AP question. A standard question from AP will go like this. Interpret the standard deviation. That's a prompt. And you go, oh, well, I'm going to give an interpretation, like an interpretive dance. It'll be free form. No, there is not a whole lot of jazz in statistics, y'all. It is not free form. Okay, there is a specific sentence that they want. And so I'm going to want you to include this prompt in your notes. Maybe I should label it. So a test, this is a test prompt. And it's totally standard. It's basically on every AP exam. Okay, and what you want to say to that is the typical distance of data points from the mean is 2.58. Now, typical distance from the mean, guys, you have to have that in the answer. It's expected that, and especially typical distance from the mean. Now, if I had more context for the numbers, I would give context in the answer as well to make it communicated really clearly, but I just made up 4 digits and went for it, so I don't have extra context. But that is something that you might even want to circle. I would say if you're going to take the AP exam, it's basically, this is going to come up, okay? It's one of those things that's just going to be there, and it's not hard if you've studied just a little tiny bit. So just a little bit of studying, and that's going to be basically free points for you. All right, the 5-number summary and the interquartile range. And those are our last 2 things today. I'll show you a little bit about the calculator and then we'll be done. The 5-number summary is the following 5 things. Oh, except don't write in highlighter. That's a bad habit. It is the minimum value, the quartile 1 value, the median value, the quartile 3 value, and the maximum value. Now, what's with this Q1 and Q3 business? Q1 is a point where 25% of the data fall below this point. That's you have to think as if you wrote a list out of all the data in a data set from smallest to largest. So 25% of data fall below this point, whatever that number would be, and that's how it's defined. You'd count up the lowest 25% of the data. So fall below this. And Q3 is the same thing, but on the other side, it's 25% of the data fall above this, or 75% below. And the median, I don't know if you'd ever thought about, that's 50 above and 50 below. So 50-50 on each side, then you got 25-75, 25-75, min is the lowest, max is the largest. The interquartile range, very similar to range, it's just Q3 minus Q1. And the reason that we include something like that is it is more resistant than the range. Okay, it's not as susceptible to outliers. So one outlier can totally destroy the range. It doesn't have a tendency to destroy the interquartile range or the meaning of the interquartile range quite as much. I do want to add one thing here, and that is this. I was doing a Google search the other day trying to prepare for this lesson, and I typed in average income in the United States. And what was surprising to me, because typically Google is really good, it would not give me the average income in the United States. In fact, it kept redirecting me, even though it seems like it's being nice here and saying, did you mean average income in US? Yeah, fine, average income in US, whatever. Actually, down here, if you look at the results it gave me, and I just included the first one, it was only willing to direct me to the median household income. Now, why do you think that is? They're not going to tell me the mean. So remember what we saw in the previous lesson about the shape of the income distribution in our country? It has a serious right skew. So in ours, we've got basically a bunch of people down here and a few people at the top, but it really gets out of whack because y'all, most people are under 100,000. Or most households, I should say. In fact, they show it here, the median, and this was as of 2016, was 59,000. That's for a household, not an individual, by the way. So an entire, and sometimes there's only one working person in a household, of course, but that's what that statistic is measuring. It's per household of people. You have to understand that there are some people up here in this graph that are like big time money, right? You have the Bezos and the Gates of the world and the Zuckerbergs and people of that nature that have these really extreme values, very similar in the beginning of this video where I put the person with 250,000 in. Guys, this is basically what it is in our country. It's that same thing. So the average, I don't know what it is, but the average has got to be like $200,000, $300,000 or $400,000. Now think about, we talk a little bit about how statistics can be used to mislead. So if we say the median is 56,000 or 59,000, and the mean is, and guys, I don't have the actual, I'm going to make it up. Okay, so 200,000. I know that because of the skewness, it's going to be bigger. Now you say, why do you know that, Mr. Boyden? Well, look, guys, you have these big old values here, and we said the mean was less resistant than the median. So these big values are going to drag the mean to the right. That's another way of thinking about skewness. In a right skew, the mean is going to be to the right of median. In a left skew, the mean is going to be pulled to the left. It's more easily dragged by those extreme values. Okay, so that's the skew direction will always be the direction that the mean falls in relation to the median. Okay, so if you wanted to mislead people, how would you do that? Well, you could talk about the median. You could say, well, the median household in the United States is $59,000, and that's a true fact. And you could use that to try to paint a picture about how, like, hey, look, like a lot of households aren't making that much money. Like that's, for a lot of people, things are, because keep in mind, that means half the country makes less than this. And so they may have some challenges or struggles, and we need to be aware of that when we are doing blank, whether it's designing policy or giving grants or whatever, okay? Social programs, whatever it is. If you wanted to give a different message, you could say something like, Well, look, the average income in America is $200,000. We're the richest country in the world. We're the best country in the world. There's great prosperity for everybody, and we're doing just great. So both of those facts are true. It's true that the median's 59,000, and I don't know the actual number, but I'm guessing that the mean is much higher. Okay, and so, but just to understand how you can paint very different pictures. So this is one of those things we get into. Well, like, why doesn't the news just tell us the facts? Well, hold up, y'all. If they tell you either one of these, they're telling you the facts. But part of what we need to learn, and part of what this class does, is it inoculates you against being misled so easily, where you say, wait a minute, why are you only telling me about the mean? Should I be looking into what the median is? Maybe there's another story that it tells if I have that additional information. So that's something I want you to think about as you kind of go through your life. When you hear, oh, the average person this, or the average that, ask yourself, why aren't you telling the median? And could I look that up and see what information is being withheld? And it's not always nefarious. People are not always trying to lie. People do this all the time. We naturally gravitate toward means, for better or for worse. For the last part of our video, I want to focus on the TI Inspire calculator and showing you how to use that, because if you're taking my class, that's what we're going to be using, and it's what I think is a really good calculator for the AP exam. And so we're going to take a look at a data set here. These are the data from one of my classes recently where I asked them what their heights were in inches. And these are the data that I got. And so what I want to do is show you how to get everything we've talked about in this video in the calculator from a data set. So let's switch over to the calculator. This last part of the video is going to run like a calculator tutorial. There's really no new concepts, it's just calculator stuff. So if this is not your calculator, or if you're not interested in the Inspire, then feel free to shut off the video. But if you want to learn more about the Inspire, here we go. In the Inspire, I always start on the home screen, and I'm going to go to New Document. And often it'll ask you if you want to save your old document. That's up to you. You can make that decision. I'm about to type in these data, and so I'm going to choose Add Lists and Spreadsheets, and it's going to give me this list. The first thing you should do is label what the data are you're about to put in. You're going to have to reference the data later, and if you haven't given them a name, it's harder to do that. So I'm going to call this height because it is height data from my students. So I'm going to take a minute to type in those data, 61, 62, a bunch of 64s. Oh, and what's the next one? 66. 66, 67, 69, 69, 70, and 72, and 72 again. All right, 14 data points. Now, what I usually do first, no matter what the data are, is typically I go look at a dot plot first, and a lot of times if I've mistyped something in, that's going to let me know. And it doesn't actually let me know, but I can kind of figure it out from looking at the chart. The way to do that, hit Control Doc, because above that it says plus page. That'll add a new page here, and we want to observe our data and statistics, so that's what we're going to do, data and statistics page. Down at the bottom, if you go down and click, it will ask you what variable you want. I want height. And do those data look like a height distribution from my class? Yeah, they absolutely do. Okay, so I don't necessarily get any of the things we've talked about directly from here, but with one easy change I can. I'll click Menu, and I'm going to change the plot type to a box plot. Now check this out. So we can easily pull the 5-number summary off of a box plot. If I want the standard deviation, I don't know an easy way to get it on this screen, but the easy way to get that, in fact, we can get the 5-number summary in the same method. I'm going to go back and click back on that previous tab, although they call it a page in this calculator, and I'm going to go and find the statistics in here. So Menu, I want to look at the statistics. I'm going to go to a stat calculation, and we only had one variable, so I'm going to choose one variable statistics. We only typed in one list, and it defaults to that, and in this case it's correct. We didn't have multiple lists of data. So I'm going to accept that. X1 list, that's asking, what variable do you want us to run your stats on? I want it to run on height, so I'm going to select height. I didn't put in a frequency list, so it's automatically chosen to make the frequencies 1. I'm not worried about categories, and putting my first results column in C or the third column is totally fine with me. So I'm going to hit OK. Notice it did most of that for me. And I've got this new list over here now where I can run through a bunch of different one variable statistics. So the first one, they did X bar for me. Awesome. So that was 66. If I keep going, they calculated the standard deviation for me right here, which is nice. Thanks. I didn't want to have to go through those 14 calculations on my own. That sounded really bad. This is a different version of standard deviation, which we're going to talk about another time. N, they told me there's 14 data points, which is good. I did have 14 data points. And they're going to list out the 5-number summary, and they intentionally put it all together sort of on purpose in case that's what we needed. So min, Q1, median, Q3, and max all together just like that. And then that last one I'm not too worried about. So that's, again, just a quick tutorial on how to get a bunch of these stats kicked out for us in the Inspire. It is so much faster and easier and less cognitively demanding to, or it's not busy work as well, to have the calculator do the work for us. So I want to encourage you, anytime you need a standard deviation, unless there's some really compelling reason, please let software do it for you. We live in the 21st century, and so we don't need to be doing that by hand anymore. Hopefully that'll save you a little bit of work. Hope you enjoyed today's video, and I'll see you again next time.